slideshow. It'll go to a slideshow so that the screen becomes a bit bigger.
Say, may you please record the lecture?
You know what? Ukata class level akaita some mess. Mapinda. Akachangamuka. Very good.
Okay, so I was saying those are the topics which we were looking at, from application programming interfaces to difference between bare and the metal servers. Then we go to redundancy in the cloud. So I'm going to take you on the first part of relevant technologies. Then when Mr. Luke comes on, you then take over, because we had shared the presentation, but unfortunately he has not yet joined the meeting. So on a relevant cloud technologies, what we are seeing in the cloud or in the modern day is that there is a growth in our data which is being generated, and also we are seeing that through our day-to-day interactions, a lot of data is being generated, and this data which is being generated, it is calling for more of increase in the demand of IT infrastructure, that is network, that is storage, as well as the processing capacities. So these technologies have been developed to ensure that we can cope up with the increase in the data which is being generated on a day-to-day basis, be it in the companies, be it on social media. A lot of data is being generated. So it is calling for the development of systems and technologies that can even accept, that can even process and bring insightful decisions. You can go to the next slide, application programming interface. Okay, thank you. Application programming interfaces refers to the set of rules and protocols that allow different softwares and entities to communicate with each other. Like what I was saying in the previous slide, the day systems of IT, we are seeing more data coming, and it is coming from different sources. Some it is coming in form of video, some it is coming in form of tables. So for us to retrieve and process that data, we cannot process that data using traditional methods. So there is need for the development of application interfaces where different programs and different systems can be able to communicate with each other so that they can exchange information. We can build our data lakes as well as data warehouses for analytics, for us to get insightful decisions. During these days where we are living, data is now more valuable. We have seen a very good example in the field of soccer, where we see our players, they will be wearing some digital vests or IT vests, which will be generating data in terms of the pace, the number of passes which they have completed and everything. Such data is then now being used, and we are seeing a scenario where we are having that vest generating data from the board of the player. We also have chips in the soccer balls or in any balls which they will be using, generating also another data. We also have cameras generating also another data. So there is a need for us to have an API which will enable us to integrate all those sources of data so that we can have a better communication and insightful decisions being made. We are seeing that my players in soccer, they differ in terms of their prices with regards to the data which they would have generated. It turns out we are no passes akawanda, we are any speed rate yakawanda and the likes, and any work rate yakawanda, because of these insightful systems that have been developed. So these APIs, their role is to integrate and ensure that softwares, they communicate with each other when they are sharing data in the servers. The next slide. So what do we use APIs for? We use them for sharing resources over multiple cloud providers. They also provide and manage the cloud hosted infrastructure, that is our servers, that is our network, as well as our nodes which are connected on the cloud. So with these APIs, we'll be able to manage the infrastructure so that we don't have a scenario where we have a lot of faults being taking place, or a lot of system downs, or where the system will fail to cope up with the processes that will be requested from the nodes. Then also we can use them for streamlining cloud security. You know, when data is being shared from one source to another source, there is a problem of security, either through intrusion or internal or external intrusion. So for us to ensure that there is a stronger security, we use this application or a set of rules so that there is a tight security in terms of the data. Then also they are used to automate disaster recovery. Like in the case that one server goes down, for the system to remain up, there is need for that communication with another backup server, which would have been created. And it is the role of these APIs to ensure that the system will always remain up. Like in the case of banks, you see, we despite the power challenges which we are facing in Zimbabwe, despite of a lot of challenges which we face, we still see that transactions, they take place on a daily basis. We may have a short glitch for maybe 2 to 3 hours, but later on we see the system up. It is because of the duty of the APIs. They will definitely connect us to the next server where the data would have been saved through the redundancy process, which we are going to explain in the next slide. Then in the next slides to come, you can go to the next slide. Hello, Mr. Luke. Mr. Newton, you can go to the next slide.
That's the next slide.
On the uses of APIs. I think my system is not showing the next slide. The one on types of APIs.
Is it true, Ms. Newton? Can you move to the next slide on uses of APIs?
Okay, while he is still sorting, let me just browse through the next slide because I'm opening it on this end. We have the types of application programming interfaces. There are basically 3 types. They are classified according to the level where they are being deployed. We have the first level, which is called the infrastructure level APIs. These are known also as the infrastructure as a service, which we let APIs, which we discussed in the previous lecture, where we were discussing that we can have the cloud system having infrastructure being deployed or being the one which will be sharing. So on the infrastructure level APIs, they are there to manage cloud-based hosted infrastructure such as servers, storage, security, as well as networks. That's what we call infrastructure level APIs. That's where they are being deployed so that we will be able to manage our cloud infrastructure. Then the next type of APIs, we see them as service level APIs. They are also known as platform as a service APIs. They connect infrastructure to third-party platforms for application development, as well as enabling developers to access tools and operating systems, softwares, and the databases. For example, I still remember that yesterday we were discussing on the aspect of Google Play Store, whereby we were saying, can we say Google Play Store is infrastructure as a service, software as a service, or application as a service? You see, when we're talking of service level APIs, they are just deployed so that developers can access tools that are stored in a certain software so that they can develop their systems, they can also test them. So that's what we call a service level application programming interfaces. Then the third type of APIs is that of software as a service, where we connect to the infrastructure so that we'll be able to use applications that are managed by third parties, so that we have applications that are running on another servers. So it is the role of these APIs that we can access, for example, Microsoft 365. We access it and we then make use of it so that we can do even document creating, do our PowerPoint slides. Then we save them also on the cloud. Then when we have another machine which is different from the one which we're using, we can even access them remotely from one point to another. So those are what we call application level APIs. They are deployed so that we can access cloud-based applications. Then on service level, they are deployed so that they can enable system developers to develop applications, to access tools which they use to develop applications. Mr. Milton, have you managed to move to the next slide? I'm still seeing the uses of APIs.
Okay.
You may stop sharing, then you reshare again so that
okay,
it can move.
Yeah. Which slide do you want? The types of APIs?
Yeah, you go to the tab, then we go to the next one.
This one, the next one. Can you see my screen now? Can you see it?
Yeah, we are still seeing uses of APIs, unless it is my system.
Oh, let me just see. So if worst comes to worst, you can just send me the presentation. I can share it from this side, and I'll look on the slides as you'll be presenting.
Yeah, I think it will be easier that way.
Okay.
All right, thank you. I now see the slide. You can move to that one, which is types of APIs continued, because that one we have covered that one. Yes, that one. We also have what we call REST APIs, which are found at the level of application level APIs. They enable users to access fully built cloud application from a client connecting infrastructure to a third-party cloud-based services. Those are what we call REST APIs. Then we also have what we call SOAP APIs. They utilize the XML for messages, and they are known for their robustness in terms of security features. They are often used in enterprise environments where the issue of security needs to be strengthened. So those are the SOAP APIs. Their system which they use, they ensure that there is high security when messages are being transferred from one system to another system, so that they reduce element of hacking and intrusion. Then we have the GraphQL APIs. They are used for query language. Then they allow clients to request only the data they need, which can reduce bandwidth and improve performance. So the GraphQL APIs, their role is that we limit the transfer of whole chunks of data. Then we just extract what we want to use. The advantage of using these ones is that we move data in smaller chunks, and it will improve in terms of bandwidth, because the storage, the capacity or the storage of the below, we improve the system. Then we do also have what we call web hooks, which allow applications to receive real-time notifications and updates from the other services. Real-time notifications and updates from other services. For example, in the case of intrusion, in the case of any update that would have happened within the cloud system, these webhooks APIs, they will give us a real-time updates. Then on that picture, we have just tried to zoom out and see some of the top 10 cloud APIs that are being used. We have the box, the virtual box, the HubSpot. Then we have the Google Cloud Storage. Then we have got the Google
Cloud Vision, then Google Translate. I think we know all about Google Translate, which translate different languages. Then we have got Lexalytics, and quite a number of them. Then the other one on Microsoft. We are going to see them as we progress. So then the importance of APIs. What role do they play and what are their importances? The first importance is that they enable integration of systems of data, which I have explained further, that we can have data from different sites, from multiple sources, which are found in different varieties, being integrated and forming one system where analytics can take place and where insights can be generated. Take case, for example, the one which I demonstrated on the issue of a soccer field, where we have data being generated by cameras, data being generated by sensors in the balls. Then we also have data being generated by the digital vest, which the players will be wearing. All that data can be harmonized through the use of APIs, and analytics can be made, which can even influence decisions. For example, the decisions, the probabilities of the teams to win, as well as also the value of the players themselves. Then they can also assist in microservice architectures and third-party services. When we're talking of microservices architectures, we are saying in the cloud system, we can end up developing some very, very small and minute systems, which we can then develop through the use of APIs. We are going to see this in the context of visualization. Then also they assist in terms of scalability. When we're talking of scalability, we are saying the purpose of going to the cloud is to scale our systems, because we are saying using the traditional approaches of data collection, data analysis, data processing, we see that our systems, they are failing to cope up with the rate at which data is being generated. So through the use of APIs, we can be able to integrate systems in cloud and also extend our processing capacities. We can extend our storage capacities to an extent that we can scale up our systems. Just consider, for example, we have a bank which will be opening up new branches and registering more customers. You find out that with the traditional system, we have a scenario where we'll be having too many transactions just taking place at the same time. So the traditional system cannot cope up with the rate at which this data will be generated. Take, for example, here, or what we are seeing in the banking or in the trading sector, where we are going cashless. Just imagine the number of transactions that are being done per minute, per hour, or per day in case of our economy. The volume is increased. So without the APIs, without cloud computing, it will be very difficult to scale up to that extent, and as well as to improve in terms of analytics or decision making. Then flexibility, the ability of a system to become more flexible is influenced by the APIs which they use. So by making a proper decision to use better APIs, you see that the system becomes flexible. The system can adapt to any changes. The system can also give the user an ability to navigate through all those systems, like the case of abstracting where data is being stored, which we see in the case of distributed systems. Then also through APIs, we can use them for faster development, whereby we are saying when we want to develop systems or when we want to develop applications, using conventional methods, we have to install all the systems which we need to use for the development of applications on a single system. Then we develop, after developing it, then we later on testing it or deploy it into another system. But through the use of APIs, we can develop them online, where we have better processing capabilities, where we have also better storage capabilities. And we can also even test them on high scales of data to see how these systems can perform, or these applications can perform on bigger storages, on bigger data sets. Unlike a scenario where we will be having a traditional systems. Then the next slide, which we are having on APIs, one of the challenges is that of security. Because we are on the cloud, the issue of security still comes again when we are using these APIs. Well, some of these APIs, they are not hosted in our systems. They are hosted on public servers. So the issue of security also comes. Then we have also the challenges of visioning. Then we also have another problem of documentation, a software that works very well, it requires proper documentation so that in the case that the person who has developed it has moved out of the organization or of the system, the others who can come, they can even just follow through the documentation which would have been done, and they will be able to go through and also develop and also debug if in the case there is an error. They can also make use of that. So you find out that with the use of cloud systems, the documentation processes will be very difficult. That's the other aspect or the other challenge which we can also face. Then here we have said the APIs may not be compatible with every cloud provider or even be designed to work across provider environment. For reason, cloud APIs are sometimes categorized by their vendor support. So we can have what we call vendor-specific cloud APIs. We are saying we are using Amazon Web Services. Also, but we then attempt to use maybe Google systems to develop our APIs, or the APIs which we are using on Amazon Web Services. They cannot as well work well without any further modification on Google cloud services. So some of the APIs, they are vendor specific, while these other APIs, they are cross-platform. They are compatible with multiple cloud providers. But those which are compatible with multiple cloud providers, they tend to be high expensive because they would have on different systems. So those are some of the challenges which we face when we are developing APIs. Then, so there is someone who is passing through where I'm parked. Sorry for that noise. Then steps to make an API connection between a server and a client. An API client, e.g. an application, initiates a request for a specific data, and this is called an API call. Then an API call is application programming interface call is received by an API endpoint, which is a server, for example. Then from the endpoint, it authenticates the request to ensure that the call is from a legitimate source and formatted using the correct API protocol, either SOAP, REST, or RPC, and the schema. Then the API at the endpoint returns the request of the data to the endpoint client. What we are saying here, we are saying how an API integrates or works. It first initiates a call from the client or from the node. Let's say, suppose I just want to request my balance remotely using a mobile banking app. When I first log in, I have to authenticate by making use of a password or a one-time key which is sent. Then after that, when I initiate the API, before it accesses the data in the server, it first authenticates whether this is coming from the relevant and legitimate source. Then from there, it formats it using a proper protocol to ensure that they can retrieve the appropriate request that is being requested. Then after that has been done, a result will then be sent to the client or to the node. For example, when we are requesting for the balance, we just say request the balance, then the system processes. After processing the system, we'll then see a return message also coming as a balance. We see this API is also integrating the USSD, which we normally use, the star 44 what those codes. You see them, they access a server, but we are sending a signal in form of a text. Then when a server accesses the core, then it returns the message after authenticating and changing the protocol to ensure that the data is returned in the correct format. The next slide, please. The next concept is that of thick and thin clients. Here we are saying the way we access cloud services is often determined by the type of the client we use. There are what we call thick clients, which are software applications that require significant resources and functionality to operate. They often offer more features and more robust experience, but they are less compatible with the different devices. Then when we're talking of thin clients, these are lightweight applications that require minimal resources and are designated for accessibility and efficiency. They are often web-based or mobile-friendly and focus on delivering core functionality without sacrificing performance. So basically, the what we are seeing from that slide is that the difference comes on the sense that The others, they require significant resources and functionality for them to operate. Those are what we call the thick clients. While it's the thin client, they use minimum resources and are designated for accessibility and efficiency. The next slide. Then, thick clients are also known as fat clients applications that perform the majority of processes on the client side, and they require substantial resources, which include the CPU, memory storage, or the memory or the storage on the user's device. Then thick clients handle most of the data processing locally, reducing the load on the server. The CPU and memory of the client where the initial call is being done. Then they are typically installed on the user's device. That can be a laptop, a desktop, or a mobile application. For example, we have the Microsoft Office, then mobile app, we can have club connected games. Then enterprise software like customer relationship management systems. Then in terms of thin clients, they are lightweighted, like I've said earlier on. They heavily rely on the server for processing and storage. They typically require less local resources, and they rely on a remote server for data processing and storage, and they require minimum local resources. They only need a browser or a minimum software. They access cloud resources. For example, we have Google Chrome, Mozilla Firefox, or Google Workspace or Microsoft 365. So we see on thin clients, bulk of the data will be stored on the server. While it's on thick clients, bulk of the data of the application will be stored on the client, and the processing will be done on the client first. And what is just sent is a signal to the server, either to store or to retrieve a specific data. So in terms of that, we see that they require a lot of memory.
Sorry, Garland.
Yes.
Maybe you can rest just for a little while. I think Roka is now here.
Okay.
Or take over from the comparison. Right.
All right. You can take from the comparison, then I come back with other points. Mr. Luke, you can now take off.
Thank you very much, and greetings to everyone. Sorry for the delay. I will move without further delay. Comparing these clients, the fat and the slim clients, actually, from the feature point of view, we consider the thick ones as fat clients and those thin ones as slim or lean clients. In terms of data processing, with the thick clients, there is local processing of data, which therefore means, as explained earlier on by Garland, that we need to have strong hardware that can stand up to speed and that can also sustain heavy duty work. And with the thin clients, because there's nothing much done or processed at the local machine, but the bulk of the work is done at the server level. It then requires just a basic hardware and probably software as well, since the bulk of the work is done at the server level. It is very rich and responsive, the thick clients, in terms of user experience, where with the thin clients, it may be slower due to server reliance, because the server may not be anywhere in the vicinity in terms of geographical location. There may be no need for communication through the internet, and any glitches on the communication line will make things slower. The thick clients, because it's this machine standing close by, it can work offline, yet there is limited or no offline capability at all for the thin clients. To maintain the thick clients, it requires some individual updates, but for the thin clients, this is centralized and it is done mainly at the server level, where the maintenance is done for use. For resources, there is a requirement for heavy duty hardware. For example, the CPU, the storage, the RAM should be that much used for the thick clients so that it can do the local work effectively. But for the thin clients, it's just minimal, something that can actually just allow communication to the server, and all the work now is done at the server level. For installations, if any, it is the installations are done locally on the local machine for the thick clients, and for the thin, there is minimal, if any, installations that are required. Usually, it's web-based because it will be getting the resources from the server that it will be connecting to. In terms of security, it is more security threats as compared to thin clients. I remember we talked of security yesterday, looking at if using the remote or cloud services is more secure than using local. So it depends on the scenario usually. And my argument yesterday was like, for the local one, it's less secure because an organization has got its expertise. For example, it's an organization that is servicing vehicles. It has expertise in servicing vehicles, but no expert in terms of computer resources and computer resource management. So this one, we can overturn it. And then for the thin clients, there are less security threats with the assumption that the end cloud service provider has got all the necessary security gadgets and also security systems that can protect the user as well. For the purpose of examples, we've got desktop applications. We also have our phones, which are the mobile applications that we use, and these are considered as thick or fat clients. And for the thin clients, we have the cloud-based productivity suites. We have the web browsers, the likes of Google, the likes of Yahoo, and the Facebooks that we like utilizing ourselves. Then from there, another aspect is broadband in cloud computing. So broadband internet connectivity allows all users to access the services that are found in the cloud, which means it allows connection between the user and also the cloud service providers that they have. Broadband usually is very reliable to utilize high speed, and this also enables seamless communication or simplified communication between both the clients and the cloud service providers. Next slide, please. Then there's different types of broadband. We have got the digital subscriber line, the DSL. This uses a telephone line to connect to the internet. We also have the cable modem, then the fiber to home, FTTH. I'm sure some of us have used them in the organization, the FTTH. If I remember well, it's Liquid that was providing this, or it's so, if I remember well. Then we also have the mobile broadband. Remember, we all have smartphones that we are using today, which we utilize also to offer this. And then we have the satellite broadband as other types of the broadband. For the characteristics of this broadband, you find that they have high-speed data transfer rates. They also have low latency. They're reliable, and also they offer room for scaling up, which means scalability. Next slide, please. To access broadband, there are different technologies that are then used. One of them being the now common 5G, 5th generation wireless network technology that everyone is currently using, I would assume. Then we have the Ethernet, where we are talking of a local area network where there are wired connections that feed connection to the gadgets around. And then we have the Wi-Fi, which is a wireless network technology, which connects devices wirelessly to the internet. And lastly, the LTE, the common LTE long-term evolution, which also is a wireless communication standard for the mobile broadband as well. Thank you. And next slide. What is the impact of broadband on cloud computing? It actually enables cloud adoption because it connects the cloud service provider to their clients. And then it supports cloud-based applications and also enhances user experience since it makes sure that there's some seamless communication as spoken of earlier. They are used for streaming services as an importance, and they also ensure that there is improved data transfer because of the high speeds that are there in such a way that a user will not notice that there is a lag between the time they have requested for some information or data and also the time they received a response from the responding server. And this then allows real-time collaboration between the clients and the servers a sweet way. Next slide, please. Okay, so I'll end here and let any of my colleagues take over. Thank you, and over.
Thank you, Mr. Luke. I think I can go through, but sorry for a little bit. Maybe you have a little bit of feedback, but I'm just traveling for a short distance. Then I will be settled. We do have the concept of data centers. It was tackled by the first group of Mr. Polycarp and team, but we will just fly past some few aspects from the data centers perspective, what we found out during our research. Then we quickly move on to the next topic. So from our previous discussion, we agreed that, or we noted that a data center is a physical room which is built with a lot of IT infrastructure, that is starting from the servers, the cooling systems, the network, the power systems, and mainly which have been developed to share resources with the different clients. But initially, when they were developed, the data centers, they were owned and tightly controlled on premises. But because of the fast growing of data and the need for integration of data, we see that they are now being owned by cloud service providers, and we now have public data centers. We have got the public cloud, private cloud, and everything, which are controlled by these data centers. The next slide. So this first slide, we're just talking on the definitions of data centers. Then let's go to the next slide. Mr. Milton, next slide.
Yes, we are on the next slide, the key features.
All right. On my part, it has not yet moved, but on the features of key features of data centers, we have servers, we have storage systems, we do have network equipment, we have cooling systems.
No, Mr. Milton, data centers, not on the key features.
Sorry?
We are still on data centers, not on the key features.
Oh, it hasn't
So
moved.
the work class is still on data centers.
Okay, let me try to reshare.
Okay, so those are the key features which were thoroughly explained by the previous group, which we have presented before us. But basically, what is more important is that these concepts, the servers, the storage systems, and the equipment and cooling systems, they will be integrated in such a way that they give us efficiency in terms of the use of the data centers, because the profitability of developing a data center or the efficiency of the data center, it lies on the integration of its resources. If its resources are not properly integrated, we will have a challenge whereby they will not be able, or they will not be in a position to share or to give the clients the maximum use which they have been developed for. So for us to have that, we should have a scenario whereby we'll be having these systems, the servers, the storage systems, and the network equipment being properly integrated to ensure that there is efficient data retrieval and data storage within that particular data center. And also that data center should also have the ability to communicate with other data centers, so that they provide the element of integration as well as the element of data sharing. Then we go to the next slide, please. Okay, on the types of data centers, here we saw that there are basically four types of data centers which we have come across with. We have the enterprise data centers, which have been developed by a single organization, and they are designed to make specific business needs and can be located either on premise or on offsite. Whereby we are saying on premise, the premise of the clients, while on the case of offsite, they will be shared. Then we have what we call co-location data centers, which facilitates multiple organizations that can rent for their servers and the networking equipment. We will see, for example, in the case of our country where we have mobile telecom operators, Econet, Tel1, and Net1, we can see them developing a data center which they will be sharing the infrastructure in terms of the house, the power systems and everything, whilst they will be connecting with their clients. So that's what we call a co-location data centers. Then we have what we call cloud data centers. They've been built specifically to support the cloud services. We have example of the Amazon Web Services, Google Cloud, the Microsoft Azure, the Oracle. Those have been developed so that they can facilitate a connection with the cloud, with the cloud services. Then we have what we call edge data centers, smaller facilities that are located closer to the end users to reduce latency, which is the speed at which data is retrieved from the system, and also the speed at which the queries are processed. Then the performance and applications that computer which meet real-time processing. Then we go to the next slide of the role of in cloud computing. By Mr. Paul. Or we procure resources on the cloud based on demand, rather than just say we want a server which has got a storage capacity of 4 terabyte or 10 terabyte. We just procure and pay as we go. So the first aspect which data centers play is that of scalability, where an organization can scale up the resources from the data center when they need it and later scale down when they no longer need it. Then reliability. Modern data centers are designed with redundancy in power as well as in cooling and connectivity, so that there will be real-time connectivity and real-time processing. Meaning to say, in the event that there is a challenge, the user can be able to switch from one data center to another without having any loss in data or any loss in connectivity. Then the other aspect is that of security. These data centers, when they were developed, the primary objective of developing these data centers is to ensure that there is security, because once the data center is developed without security, we will see a situation where we will not be able to have more customers as an organization which have developed a data center. So to ensure that there is enough customers coming to us, we also have to have a proper secure data centers. Then the last one is on performance. Proximity to data centers enhances performance on the cloud applications, and as data can be processed and retrieved very quickly. Then the next slide, it is on the categories of data centers. This one was not touched much by the first group. We have the first one, which is called the first tier, which is just a basic facility. The power source, single cooling system, no redundant network components, limited security measures. Then the second tier is a single site with redundancy. The redundancy will be in power, whereby it will be having dual power feeds, so that in the event that one power supply fails, the users can, or the data center can just switch to another power source. For example, we'll be having a power source from the main grid, or then we have another power source maybe from a solar system which is on site of the data center. So when the grid is off, the system will automatically switch to the local, which is the solar system, and this will improve in terms of connectivity and availability. Then also we also have the redundancy in terms of cooling systems and network components. The issue of network components, we also discussed it yesterday, whereby we were saying we will not be relying on a single backbone. If one backbone fails, then we will automatically switch to another backbone. That is the two-tier database system. Then the three-tier vendor, we have a modular single site with redundancy. So we'll be having multiple redundant power sources, multiple redundant cooling systems and networks, but with enhanced security measures. So this one, on the three-tier, the aspect of security is now being introduced and is now being strengthened. But we'll be having it on a single site with redundant in terms of power and system. Then the fourth tier, we have got multiple redundant and single site. We have got multiple redundant power sources, redundant cooling systems, redundant network components, and extensive security measures. Then the fifth one, we've got multiple redundant and multiple sites. The fifth aspect here, we are seeing that we'll be having a data center which will be having multiple sites with the data being redundant from one site to another, meaning to say we'll be maintaining a copy of the data from each site in each and every site to ensure that there is reliability. Then our next slide, please. Then the future trends which we are seeing in the data centers. The first one is the concept of hybrid cloud solution, where we offer security and control on-premise data centers along with flexibility on the cloud. So here we are saying what we are seeing in data centers, we data being stored on the premise and also data being stored on the private cloud, but with the issue of strength of security being strengthened. Then the other issue which we are seeing is that of automation and use of artificial intelligence. Previously, when data centers were developed, they were tightly controlled, which being on the premise and specifically serving for an organization and everything. But now we are seeing that by the introduction of automation, we can see the data being redundant across different databases or different data centers. Sorry. Then we also have the issue of automation, whereby we are saying through the use of artificial intelligence, even if there is a disaster, the rate at which the data center recovers, it will be very high because the systems, they are now developed and they are now being monitored through the use of artificial intelligence systems. For example, the systems, they are trained using machine learning models so that they can even detect the anomaly prior before it has even occurred, and develop a system that will enable the system to recover out of that. Then we have got green data centers, whereby we are saying, because data centers, they consume a lot of power, but in recent mode, we are seeing that there is now more advocacy of use of green technologies, use of green or clean sources of energy, such as solar, such as hydroelectricity. That is the one which is now being used in the data centers. Then we also have the concept of virtualization, where there is sharing of servers. When data centers were introduced previously, we see that the server was developed mainly maybe for a specific task or for a specific concept. But with the modern trends, we are seeing that there is the element of virtualization, which we are where we see a single server being splitted and being used by different nodes or having operating systems. Then the next slide, please. Mr. Milton, next slide.
Yes, I've moved. Confirm you can see it.
Yeah, now we can see. All right, the next topic which we also looked on, it was on visualization in cloud computing. So visualization, by definition, according to Anon, visualization is a process that allows a computer to share its hardware resources with multiple separated environments. With visualization, organization between operating systems without the need of rebooting. A scenario without visualization, for you to switch maybe from Linux to the server, you would need them to reboot. But we are now seeing this operating system experiencing in terms of visualization. So from those illustrations, if you look at the bottom illustration there, the traditional architecture, we had hardware, then we had the operating system, then we have application. But now with the concept of visualization, we can have a virtual layer, then we have got multiple operating systems and applications running on the same hardware. So that is the concept of visualization. Then on that top illustration, we are seeing different types of visualization, such as desktop visualization, server visualization, storage visualization, network visualization, as well as application visualization. You can go to the next slide where we are going to expand more on those concepts. No, you can skip that one. That one is just a summary of comparing the different types of visualization. Then we go to the hardware visualization. Hardware visualization is the technology that allows multiple operating systems to run concurrently on a single physical machine. which was not possible in the previous architectures of computer systems. We can have Linux, we can have Microsoft running on the same server, but using the same hardware. That is what we call the hardware virtualization. So in visualization, two basic categories or basic types, which is called type 1 hypervisor and type 2 hypervisor. So in hardware visualization, we use what we call hypervisors. And what are these concepts? These are scripts that have been developed so that we can run different systems on a single server. They are more or less like a software which are developed, and when these softwares they are developed, they are deployed in a server. That's when we now have these categories of type 1 and type 2. The type 1 hypervisor, it is a scenario where we have the hypervisor being installed on the hardware directly. Then we have different operating systems running on top of the hypervisor. Then on the type 2 hypervisor, we have a scenario whereby we have a host operating system running on the hardware. Then we have the hypervisor being installed on top of the host operating system. And we then now have the guest operating system installed on the hypervisor. Examples of hypervisors, we have the VMware ESXi and the Zen hypervisor, as well as Microsoft Hyper 5 and Oracle Virtual Machine Server. Those are some of the examples of type 1 hypervisors. Then in the case of type 2 hypervisors, we can also have Oracle VirtualBox. We can also have Parallel Desktop as examples of type 2 hypervisors. So this is how hardware is virtualized in a cloud. The type of visualization is that of memory visualization. In the case of memory visualization, we are abstracting the physical memory resource for virtual machines and allowing them to use the memory dynamically. By being dynamically, we are saying they will be using the memory according to the requirements of the virtual machine. If the virtual machine requires more memory, we will see that virtual machine being also given more access to the memory. So that is the concept of visualization. And if you look at that illustration, we have the physical memory, which we have. Then from the physical memory, that physical memory can then now be splitted according to different virtual machines. We have got 2 virtual machines. Then we can also be splitted according to the processes that are being run on the virtual machines. For example, if virtual machine 1 has got 2 processes that are running, the same memory can also be shared within those 2 processes that are running. Also, on the case of memory visualization, another powerful tool which we see is that of paging, where we make use of the physical storage, the hard drives or the storage drive as part of the memory. We take part of it. I think this one we see it in mobile phones, whereby you see a mobile phone, they will say it has got 8 gig RAM, 8 plus 3, where 3 gig will be a virtual memory. So this is the context of memory virtualization, which we can see. The benefits is that they balance the shortage of physical space. They are inexpensive virtual memory. They support multitasking and collaboration, and they avoid memory fragmentation. Then they also enhance data security. How do they enhance data security? We are saying each virtual memory will be having its own, each virtual machine will be having its own memory in terms of the RAM which it will be operating. Then we have got the storage visualization, whereby we are saying we consolidate the physical storage which we have in the operating system as a single storage. Then this approach simplifies storage management and enhances storage efficiency and improves disaster recovery. So from that illustration, if you see, we have got 2 servers there. Then from the 2 servers, we have got what we have created, which is called virtual volumes. But these virtual volumes, they are being created from different or multiple storages that would have been created. For example, we have got 3 storage devices that are integrated there. Then through the visualization layer, the hypervisors which we were talking of, we have 2 virtual volumes. Volume 1 saving server 1 and volume 2 saving server 2. That is the concept of storage visualization. The benefits of storage visualization is that it is highly scalable. It allows easy addition and deletion of storage without affecting any application. And also it enables data migration. We can migrate data from one volume to another without affecting or without having challenges on how the users view the data. So that is what we call storage visualization. Then we can go to the next one, that is data visualization. Data visualization is a powerful technique that offers unified view of data from diverse sources, eliminating the need of physical data movement. This is according to Patrizio in 2021. So on data visualization, this concept was, we also experienced it in parallel and distributed database systems, whereby we see that data is coming from different sources, then it is visualized, and we can just see it in multiple, as a unified view. Like, for example, on that illustration, we see that data is coming from the enterprise resource systems. It is coming from databases and data warehouses. It is also coming from cloud applications, XML files, Excel files. NoSQL data is coming, also PDF and docs. Then everything through data visualization, we'll just see from the data consumers. We can even see analytics being taking place. We can also see data on the mobile web. But with regards to where the data is being generated or where the data is coming from, it will be coming from different sources. So that is the element of data visualization, and it eliminates the need for us to move data from its source, reducing storage and maintenance costs while enhancing agility and scalability. Then the next aspect is that of network visualization. On network visualization, we are saying we have a physical network which we are having, which we are connecting on the cloud. Then there comes a situation where we create, through the use of an application, we create virtual networks that operate independently on the physical infrastructure. So the idea there, we are saying we can have a public network, we can have a private network. Then if we join the two, we can come up with different virtual networks, which we'll be using to access our data. That is what we call the network visualization process. So the benefits of network visualization, they include a creation of visualization environment that adapt seamlessly to evolving business needs. It delivers higher speed, automation, and administrative efficiency that is not achievable with only a physical network. Separating the physical network from the virtual network, it also isolates the physical network from any virtual network, thus enforcing network security. Normally, we know that most of the intrusions, they come through the network. So if we develop these virtual network systems, we will be able to enforce security from our networks, because we'll be able to monitor our systems. Then the other aspect which we have is that of server visualization. Then on the server visualization, what we see there, we have what we call host servers, where the visualization takes place. Then we have the hypervisors, which we have explained on hardware visualization, which allocates resources between different virtual machines. Then we have what we call the virtual machines. So the aspect of server visualization, we are having one server serving or having multiple operating systems being installed on it and being used by different clients for different purposes, which was very difficult in the previous part, whereby if a server was developed for a specific use, it was going to be used for that specific use. Then we have what is called the bare metal servers. The bare metal servers, these are dedicated resources that exclusively access all the 4 resources for the server, including the CPU, the RAM, and the storage. And one of the critical aspects of bare metal servers is that they offer higher performances, because they are just dedicated for a specific task. So bare metal servers, they differ from virtual servers in such a way that this is just a physical server which we have, which will be used for a specific purpose. Then also they are customized according to specific needs of the clients, or they are tailor-made for a particular organization. Then in terms of security, they are enhanced security due to lack of visualization and reduce potential vulnerability that comes with the visualization. Because from visualization, we are seeing different clients entering or using one common server. So we can have a challenge of intrusion coming from different clients. But in terms of bare metal servers, they are custom made for a particular organization or particular use. So in terms of the differences, yes.
Is it possible if we skip this slide, maybe we can share the presentation so that we move on to redundancy in the interest of time?
I think this is the last slide. Let me just go through, then we move on to the next. So this is just the difference between bare metal and the virtual servers. They are different in terms of that. The bare metal is a physical dedicated server. Then the virtual, they are created through hypervisors where they share physical resources. Then the resources are dedicated to one user or organization under bare metal, but resources, they are shared among multiple virtual machines in terms of virtual servers. Then their performance is very high. They are impacted by other virtual machines in terms of virtual servers. Then there is full customization of hardware and software under bare metal servers. But under virtual, there is limited customization. Then on scalability, they require provisioning of new physical servers. While on virtual servers, we can scale them up because the systems will have been, the physical hardware will have been connected, so we can just scale them by increasing the capacity which the virtual machines will be using. Then, in terms of cost, they are very costly. The bare metal servers, because they are developed for custom made. But in terms of virtual servers, they are less costly because they apply the element of pay as you go. You use the resources as according to your needs. Then in terms of performance, higher performance, in terms of use cases, bare metal servers, they are used for higher performance applications like gaming server, where there is strict compliance requirements and everything. But virtual servers, they are used for web hosting, development and testing on environments and production workloads. I now hand over to Milton and Bridget to look into the concept of redundancy. I thank you.
Thank you, Gallant. Good afternoon, team. I'll proceed. We'll be looking at redundancy in cloud computing. So redundancy as a definition in cloud computing, it refers to the practice of duplicating components or systems within a cloud infrastructure to ensure high availability and fault tolerance. So we'll look at high availability. High availability cloud computing. This is a computing infrastructure that allows a system to continue functioning even when certain components fail. And its goal is to minimize downtime and ensure that services remain available even one or more components fail. There's also fault tolerance, that is withstanding hardware or software failures without impacting services. High availability also allows quickly recovery from natural disasters, data center outages, or other catastrophic events. The importance of high availability is that it ensures that critical applications remain accessible, which is vital for maintaining business operations and customer trust. It reduces the risk of service interruptions, which leads to higher user satisfaction and confidence in the service of the customers. Many industries have compliance requirements that have mandate certain levels of uptime and data availability. Then the key concept of high availability, that is the increased uptime, the failover, redundancy, improved reliability, enhanced disaster recovery. So we are saying on increased uptime, the percentage of time a service is operational, that is the higher availability system. Typically, it aims at 99.9% or higher than that. So on failover, the process of it is the process of switching to redundant or standby system upon failure of the primary system. How to achieve high availability? There should be load balancing, that is distributing of incoming traffic across multiple servers to prevent any single server from becoming a bottleneck or the point of failure. Then we can also achieve through clustering, that is grouping multiple servers to work together as a single system. And then we've got geographical redundancy, whereby there's a deployment of systems across multiple geographical locations to mitigate the risk associated with natural disasters. And then we also have data replication, whereby we keep copies of data in multiple locations to ensure data availability and integrity in case of failures. Then these are the disadvantages of high availability, that is complexity in designing and managing the high availability architectures, and this may require specialized knowledge. The costs, implementing redundancy and failover mechanism can also increase operational costs, especially for smaller organizations. And testing failover, regularly testing failover process is essential, but it can also be disruptive and challenging to execute without impacting the users. So from high availability, we move to business continuity planning. So this is a process of creating a strategy to maintain and restore business operations in the face of disruption, such as natural disasters, cyber attacks, power outages, or hardware failures. So the importance of business continuity plan is a risk assessment. We need to identify potential risks and outline strategies to mitigate them, ensuring that an organization can respond in the event of disruptions. Then we need to minimize downtime, and then regulatory compliance, customer trust. In many industries require DCB to comply with regulations regarding the data protection, and also they need to demonstrate to customers and stakeholders that an organization is prepared to handle crisis whenever disaster struck. Then the key components of BCP is that the risk assessment, they need to identify critical business functions, potential threats, and the impact of disruption. Then we've got the business impact analysis. We need to analyze how different disruptions affect operations, and we need to also determine recovery priorities and setting recovery time and recovery point objectives. And then we've got the strategy development. We need to formulate the strategy to maintain operations. This may include redundancy, cloud solution, remote work policies, and alternative communication methods. We've got to plan development, that is to document the procedures, roles, and responsibilities for responding to disruptions. And all this also includes the communication plans and the recovery steps that will be taken. Then we've got the testing and maintenance. We need to regularly test the business continuity plan through drills and exercises. And then redundancies in business continuity planning. Sorry. So these are the challenges of business continuity planning. This includes complexity, costs, adapting to change, testing challenges, data security, compliance, and vendor reliability. The BCP can be complex in developing and maintaining a comprehensive BCP plan. It requires collaboration across different departments, and also the costs may be significantly high. And then adapting to change, the organization must continuously review adapt to their BCP, to adapt to new threats and technologies, and also the business processes. Will move to hardware level redundancy. This refers to the practice of having multiple hardware components such as server, storage devices, and network equipments in place to maintain functionality in the event of hardware failure. And the benefits of hardware failure is that there is increased reliability, whereby redundant hardware components help prevent the services interruption, ensuring continuous availability of applications and services, minimize downtime. In the event of hardware failure, redundant system can take over. This can significantly reduce the downtime, and it also maintains the business continuity. And then we've got simplified maintenance, risk mitigation, enhanced disaster recovery. By eliminating single points of failures in organization, an organization can reduce the risk associated with hardware malfunctions. Then the types of hardware redundancy, we've got the server redundancy, we've got the storage redundancy, and network redundancy, and power redundancy. On the server redundancy, there's the use of multiple servers to host applications or services. If one server fails, traffic can be redirected to another server. Then on storage redundancy, there's the implementation of RAID, that is the redundant array of independent disks configurations. This is done to protect against data loss due to disk failures. Data can be mirrored or stripped across multiple disks. Then on network redundancy, we need to utilize multiple network paths and devices to ensure connectivities. This can include redundant switches, routers, and internet connections. And then on power redundancy, we need to have backup power supplies such as UPS and generators to ensure that hardware remains operational during power outages. So implementing in cloud, that is the major cloud providers like AWS, Azure, Google Cloud implement hardware level redundancy as part of their infrastructure. These include redundant servers, storage systems, and network components within their data centers. Then availability zones. This provides providers often use multiple availability zones on data centers in different geographical locations to ensure redundancy. If one zone experiences issues, service can automatically fail over to another zone. Then we've got the load balances. Cloud environments frequently utilize load balancers to distribute incoming traffic across multiple servers, ensuring that if one server fails, the load can shift to other servers. So the disadvantages, the cost, the complexity, and the maintenance. Implementing hardware redundancy can increase capital and operational expenses. It requires additional hardware and maintenance. And on complexity, managing redundant systems can add complex to IT operations, requiring specialized knowledge and skills. And then testing and maintenance needs to be done regularly, and this can be resource intensive and may require planned downtime. So I'll leave Bridget to take us through process redundancy.
Okay, thank you, Milton. So I'll wrap up our presentation. Milton has already explained redundancy, why we are doing it. So basically, we are just duplicating our data so that we prevent data loss. So I'll just explain the other 4 different types of redundancies on top of hardware level redundancy that Milton has already explained. So at the back of our minds, let's just know that when we're doing redundancy, we are increasing availability that Milton talked about. We are improving performance, we are tolerating faults, we are preventing data loss. Basically, that's all we're trying to do. So under process redundancy, we are duplicating critical processes within our systems at organization level to enhance reliability, availability, fault tolerance that I talked about. Next slide, please. Okay, so we can do this in 2 different ways. We can have failover mechanisms. We can also have load balancing. So under failover mechanisms, we will be having automated systems that switch to a backup process if a primary process maybe has encountered an error. So we have one system, and then we have that system fails, then another system takes over. And then with load balancing, we'll be distributing our workload across multiple instances. For example, we can have applications like maybe Google Docs, where so many people are using Google Docs at the same time. So we can have multiple servers that will be handling the different types of incoming requests. Next slide. Yeah. So I'm not going to talk about this because I put them in an umbrella. I put them in one thing when I started, that we are basically improving performance, we are preventing data loss, we are tolerating faults. Then the disadvantages of process redundancy are that they come with increased complexibilities. They also come with cost implications, like I indicated earlier, that we might we might need multiple servers that will be processing different incoming requests at the same time. So that means more resources, thus more costs. And then we can also have issues to do with latency. Let's move on. All right. Then we also have network redundancy, where we'll be including extra components in a network. Components like routers, components like network service providers, to ensure continuous operation in case of a failure. So the same thing applies with the network redundancy. Its primary goal is to enhance reliability and availability by providing alternative paths for data transmission. Let's move to the next slides. So for the components, there's redundant network parts where we'll be utilizing multiple routers, like I mentioned earlier, or switches or connections to ensure continuous network access. Then there are also load balancers with network redundancy, where there's distribution of network across multiple servers or data centers. I'll give an example of where I work here at ZAP. We have Zoll and Tel1 at the same time as network service providers. So in the event of failure of one service provider, our system automatically switches to the next service provider. So we might not even notice that glimpse of the downtime. Sometimes we do notice it, but just for a few seconds. So that's an example of a network redundancy, where we are just having backup network service provider. Then next slide, the benefits: we are reducing the risk of network outages, and we're also improving the overall network performance for an organization. So yeah, an organization can use separate internet providers, like I've already alluded. Then the disadvantage with network redundancy: again, there are higher costs associated with it, because having to pay Tel1 and having to pay Zoll for the same service at the same time, that's costly. You know, you can just do it. You can just deal with Tel1, but because of our different types of environments and so many factors that are affecting network, we also need a backup. But the backup will come with cost disadvantages, and there's also management overhead, and there's also potential overhead. Let's move on. Then the second from last type of redundancy is the geographic one. This one is self-explanatory, where we are basically enhancing availability again by distributing resources across multiple physical locations. The data centers that we talked about by Gallant and also by Group 1. So you can have multiple data centers hosting services in different geographic locations. I'll give an example of Google, which has data centers in the North America, in Europe, and also in Asia. So this is a type of a geographic redundancy. You find that each time you want to Google, you always get an answer, but it doesn't mean that the whole system is always up. Sometimes it may be down in Asia, and then there will be a backup copy of that data in America, and you can access whatever that you are searching for on Google. So that's geographic redundancy. And then there's also multiple data centers. I've talked about them. There's also disaster recovery sites, where we have a secondary site equipped to take over operations in case of a disaster. So within the same site, you'll be having a certain site which is actually running the system at the moment. But when that site encounters any type of failure or any miscap, it switches automatically to some secondary site that will be readily available to take over. Maybe there's a disaster, let's say maybe in a certain city, and then there's the same data center in another city within that country that is there specifically to just take over in case of a disaster. Why? What are the benefits? There are recovery benefits, like I've already alluded. You don't lose your data quickly. We are preventing data loss, and we are also ensuring business continuity in the event of natural disasters like floods and fire and stuff. Then drawbacks when it comes to geographic redundancy: we have regulatory challenges, we have got data consistency, we have got also latency drawbacks. And then moving on, Milton. Then the last part of our presentation is on storage redundancy. It's also self-explanatory. We are duplicating data. We want to store our data in an alternative place so that we don't lose the data, so that we increase availability, integrity, etc. So basically, we're saying it refers to duplication of data across multiple storage devices or systems to ensure the aspects that I've talked about. Next slide, please. So on storage redundancy, we have RAID configurations, which means using techniques like RAID 1, RAID 5. RAID 1 is mirroring, RAID 5 is stripping with parity to protect against disk failures. Then we also have data replication, where we'll be regularly copying data to secondary storage locations, either within the same data center or in another geographic location. Next slide. Why do we need to have storage redundancy? To ensure data availability again, and to also prevent data loss again. Moving on. Then the disadvantages are the costs. Again, storage. When you speak of storage, it means maybe more disks, more RAM, more everything. So obviously it comes with a lot of resources, and there are some cost implications. And then there's also data management complexities to deal with the management of data so that you don't lose it. Then there's also inefficient resource utilization. So with storage redundancy, I'll give an example of Google Drive. We never lose our data on Google Drive. We have our pictures, we have everything that we upload. Why don't we lose it? Because it automatically creates redundant copies of files in multiple data centers that we're talking about. So basically that's redundancy, the hard level redundancy that Milton talked about, then the process redundancy, network redundancy, geographic redundancy, and storage redundancy. So without further ado, this is the end of our presentation. Thank you.
Thank you very much, Group 3, for the presentation. They deserve a pam-pam. All the presenters were very good in presenting, but I needed something like a simulation. Mr. Gallant, who presented on the visualizations, he was talking of type 1 and type 2. We needed something like a simulation. Class, do you have any questions to ask Group 3? Any questions to ask Group 3? Any questions to ask Group 3? Madam Shumira Inuve.
Yes, sir.
Yeah, any questions?
I don't have questions.
Mans, why? Rekutuma apichi.
I think I managed to grasp something.
Okay, thank you very much. What about say polyglot?
Good evening, sir.
Yes, boss.
Very well. I think I have no question. I just want to comment and applaud Group 3. I think they were very organized. I could follow clearly their presentation.
Thank you very much for that compliment. Even myself, I was following, I was actually learning a lot from Group 3. Maoneke, given. Are you contented?
You are now unmuted. You are now muted.
Time to digest. So what your next task, Group 3, probably next week when you'll be writing assignments, we need a simulation. Anyway, I'll do the simulation myself so that the rest of the class will understand what we were trying to mean when we were talking about the hardware redundancy, the network redundancy part of it, all those. I will do the simulations for the class. If there's nothing more to look at, class, let's meet tomorrow when group 4 will be presenting.
Yeah, thank you, sir.
Yes, group 4 will present tomorrow, but please, let's probably start at 2:30, soon after lunch, so that I'm sure group 3 might have some simulations. Group 4 now, sorry, we'll be having some simulations on load balancing, so that the class will have reward testing of those. So please make sure that by exactly 2:30, let's meet and have them present. If time permits, we'll also get to group 5 so that we are sure that this week we have covered all the presentations. Thank you.